Today's lesson is going to focus on concentrations of solutions. We have talked about the solubility of substances and explained the theoretical concepts as to why a solute will or will not dissolve in a solvent. Today, what we're going to focus on is calculating the amount of solute that does dissolve in a given quantity of a solvent. And the distinction between terms has to be noted. So solubility will be the amount of solute that dissolves in an amount of solvent, but concentration is the amount of solute per quantity of solution. And remember that solution is the solute and the solvent. And we have to be aware of that because sometimes they will ask us to solve for one or the other, assuming we understand that both of them are combined to make a solution. Solutions can be described as concentrated, okay, where you have many solute particles, or a dilute solution means that you have fewer solute particles per given quantity of solution. And when we know the exact concentration of a solution, we then are allowed to compare concentrations, but also to find the amount of solute in a given volume of solution. We may also be asked to figure out the amount of solvent. And this is where, again, we have to be aware that the two of them together combine to make a solution. There are four types of concentrations that we're going to look at in this lesson. The first one is mass volume percent. And when we are talking about the mass volume percent of something, we are talking about a liquid solution. And I know this because we are talking about the volume of solution. So this will represent the concentration as a mass of solute, which will be a solid, dissolved per volume of the solution. And it's a fairly simple calculation or formula to set up. We would say mass volume percent is equal to the mass of solute in grams. Important that we are aware of these units, divided by the volume of solution in milliliters. And because it's a percentage, we're going to multiply by 100% after. So here's an example. An intravenous solution for a patient was prepared by dissolving 17.5 grams of glucose in distilled water to make 350 mils of solution. Okay, it's important that we realize that that volume is solution. So they're already accounting for the glucose and the water together. Calculate the percent mass volume. We often use short forms like this of the solution. So we set it up. Percent mass volume is mass of solute over volume of solution. That's my short form, solution, times 100%. And then we sub in our values. So 17.5 grams. We divide that by 350 mils times 100%. And we're still mindful of significant figures here. So we're dividing out. The 100% does not count. It's a constant. And both of the numerator and denominator are 3 sig figs. The calculator tells us that we get 5%. Because of significant figures, we're going to write 5.00%. Units are not necessary because over here, when we write that we're solving for percent mass V, we know that we're dealing with a gram and milliliter unit. You don't need to state that. Here's another type of solution where we would be calculating the mass percent. So this would be for a solid solution. And we can tell because we're dealing with masses, which implies that you're dealing with solid substances. So a concentration of unsaturated solution as a mass of solute dissolved per mass of the solution. So when everything is in masses, we need units of grams. And again, it's a percentage value, so we're going to multiply by 100%. So it says find the mass of pure silver in a sterling silver ring that has a mass of 6.45 grams. It says the concentration of silver in silver alloys is 92.5%. So they're giving us the percent value here. So we're going to just set this up. So we know we're solving for percent mass. we are solving for the mass of solute over the mass of the solution times 100%. So we know the percent value, so we're going to bring it over here, 92.5%, and we might as well bring the 100% over and divide it out. We know we have to make that percentage value a decimal, and we might as well just do that right off the bat. Now the question is asking the mass of pure silver in a sterling silver ring. So we are solving for the mass of solute. So we'll leave that alone. And that means we need to know the mass of the solution. Well, the solution is the ring. And the ring has a mass of 6.45 grams. So we solve that or sub that in. And then we're going to cross multiply 6.45 by 92.5, divide by 100. And then we're going to get a mass of solute that equals 5.9, 5.97 grams. Again, keeping with significant figures. Okay, here's another percentage concentration calculation that we can do. This one's volume percent, so it implies right away you're going to be taking two liquid substances to make a solution. So you're going to have a volume of solute in milliliters, a volume of solution in milliliters. So these would be liquid solutions. So this question says, how much pure water should be added to 15 mils of pure acetic acid to make a 5% volume solution of acetic acid? So this is vinegar that we're talking about, and this is typical concentration of vinegar that you would buy in the store. Mostly water, but 5% of it is the pure acetic acid. So let's set this up, and we want to solve for percent volume. Volume now, you're most welcome to use the short forms, and we're going to do volume of solute over volume of solution times 100, and then sub in what you know. So we know that it's 5%. Let's get that 100 over here and divide it out. And then we know that it's saying how much pure water should be added. So we know that we're dealing with 15 mils of pure acetic acid, and we need to figure out the volume of our solution. So what we'll do is we don't want our volume of solution in the denominator. So I'm going to do a little trick here where I flip both numerator and denominator so that I get this unknown into the numerator. So all I'm going to do right now is I'm just going to take this and I'm going to flip both sides. So I'm going to take 100 over 5%, and I'm going to equal that to the volume of solution divided by 15 mils. So you can do it like this. You can divide both sides or multiply both sides by volume. There's different tricks to do it. Now all I need to do is cross multiply 100 times 15, divide out by 5, and I get a volume of my solution that equals 300 with a decimal mils. And that is not my answer, because my answer is asking how much pure water should be added. So remember, what we're solving for here are solutions which are made up of solute and solvent. So I have to do an extra step here. So let's number this one as number 1. Number 2 will be my volume of solvent. And what I'm going to do is I'm going to take my solution of 300 mils, and I'm going to subtract off the solute, which was 15 mils. And then when I do that, I get an answer of 285, that's an 8, milliliters. And remember, when we're subtracting, we have to keep significant figures to the fewest number of decimal places. So just watch little questions like this. They will sneak that in there and ask you for a solvent value, which sometimes you have to do an extra step and calculate. Sometimes in chemistry, we deal with solutes that are barely there in the solution. Okay, so very, very small quantities are dissolved in a solvent. And it says here, very dilute solutions that have concentrations of less than 1% mass can exist, but we need a different way to calculate their concentration, because dividing or multiplying by 100% will still give us a very, very, very small number. So what we often do is we use units called parts per million or parts per billion. You've probably heard of this. ppm especially is more common out of the two. And if you notice the formula, it's very similar to a percent mass, right? So we're taking mass of solute divided by mass of solvent or solution, and it's the same for both of them. Just instead of multiplying by 100% over here, which would still give us a very small concentration value, we multiply it by a larger value to get to a more of a whole number. So you either multiply by 1,000,000 for parts per million, or you multiply by 1,000,000,000 if it was parts per billion. But the setup of the formula, or the mathematical formula, is the same as the previous examples. So here's a great example of using parts per million, which again is the same formula we've been using all along, amount of solute over solution. Just this is more used when we have small amounts of solute particles around. So this is a classic calculation where you are testing a substance such as a fish, and you're trying to determine the concentration of heavy metal in it and then compare it to Health Canada's standard. So their maximum mercury content in fish should be 0.5 parts per million. Mercury is a neurotoxin, and people should not be consuming it. So it says when a 1.6 kilogram salmon was tested, it was found to contain 0.6 milligrams of mercury. Would this salmon be safe to eat? So we're going to calculate the parts per million and determine whether it'll be safe or not. But one thing you'll notice is that your units do not match, and we have to have units of grams. So first thing that we need to do is we have to convert these to grams. And so this is where your conversions come in handy. So we talked about this back in Unit 3. Remember that 1 kilogram equals 1,000 grams. And remember that 1,000 milligrams equals 1 gram. You need to know these, okay? You need to know those conversions. So why don't we do the 1.6 kilogram first? So if we are taking 1.6 kilograms and we want to convert to grams, I want to set this up that my kilogram unit is going to get canceled out. So I want to put 1 kg in the denominator and 1,000 grams in the numerator, and I can convert that into 1,600 grams. If I want to convert 0.6 milligrams into grams, I want to set up my conversion ratio so that milligrams will be in the denominator to cancel out, grams to be in the numerator. So I'll have 1,000 milligrams down in the denominator. When I divide that out, I get a value of 0.0006 grams. So keep track of those zeros. Now what I can do is I can set up my ppm formula, and then I'll compare it to this Health Canada standard. So we're going to take mass of solute over mass of solution, but instead of multiplying by 100%, we're multiplying by 1,000,000 because we're going to have a very small amount. And you can see that the solute is only 0.0006 grams. My solution, or my fish, is 1,600 grams. And we're going to multiply by 1,000,000. And when I do this, I get a ppm value of 0.375. And when I compare that to the Health Canada standard, it's below. Therefore, we know that the fish is actually safe to eat.